Recall, the linear system of differential equations y prime equal to a times y with the determinant of a non-zero has a unique equilibrium solution which is at the origin of our phase portrait y equals the zero vector. We studied the cases where we have distinct real eigenvalues, but in the cases where the eigenvalues lambda 1 and 2 equal to gamma plus or minus I mu are complex, the equilibrium solutions will behave differently than those real cases that we already looked at. If we take lambda 1 to be gamma plus I mu with an eigenvector v, then we'll have a complex solution y sub c of t equal to e to the gamma plus I mu t times v. And we can rewrite e to the gamma plus I mu t as e to the gamma t times cosine mu t plus I sine mu t, still being multiplied by our eigenvector v. Now, the factor cosine mu t plus I sine mu t will always have length equal to 1, and it'll be periodic. And since v has constant length, the length of our solution y varies with e to the gamma t. So in the phase plane, because the solution is periodic and the length is varying with e to the gamma t, we'll have that the solution will be periodically spiraling around the origin with a length that again varies with e to the gamma t. So let's consider what can happen as e to the gamma t varies. If gamma is positive, then the length of the position vectors for our solution will be growing. So we'll have a periodic solution spiraling around the origin that's growing larger and larger. In the case when gamma is negative, we'll have a periodic solution that's spiraling into the origin. And finally, in the case when gamma equals 0, we'll have a periodic solution that closes the loop and keeps moving around the origin in purely periodic motion. We give names to these three cases that come up. In the case when gamma is positive, we call the equilibrium solution at the origin a spiral source. If gamma is negative, we call the equilibrium solution at the origin a spiral sink or a node. And finally, in the case when gamma is equal to 0, we call the equilibrium solution at the origin a center. Since the classification of the equilibrium solution depends on the sign of gamma, and we've looked at the cases where gamma is positive, negative, and 0, these are the only three classifications of equilibrium solutions when we have complex eigenvalues. Since all solutions of linear systems of differential equations with complex eigenvalues either spiral into, away from, or around the origin, depending on if it's a spiral sink, spiral source, or center, we can consider whether the solutions are spiraling clockwise or counterclockwise around the origin. And due to the uniqueness of solutions to initial value problems, no two solutions can intersect. And thus a given differential equation cannot have some solutions that spiral clockwise while other solutions spiral counterclockwise. Otherwise, they'll have to have intersecting points, contradicting the uniqueness of solutions. In other words, for a given system of differential equations, we either have that all solutions are spiraling clockwise or all solutions are spiraling counterclockwise. So the direction of the spin for one solution determines the spin for all solutions. And moreover, determining the direction of the spin at one point is sufficient to determine the direction of the spin of one solution, which then determines the direction of the spin for all solutions. So we can find how all solutions are spinning by looking at one point. To see how to determine this, consider our earlier example given by y prime of t equals the matrix -2, -3, 3, -2 times y of t. This matrix we found to have complex eigenvalues -2 plus or minus 3i. And since the real part, -2, is negative, the equilibrium solution at the origin is a spiral sink. Now, to determine the spin at one point, we want to look at the direction of our solution at one point. In y prime, evaluated at a point, gives the vector tangent to the solution y at that point. So let's look at the point y equals 1, 0 and compute y prime to know the direction of the tangent vector. I want to note that we can choose any point other than the origin for this. We simply picked 1, 0 for its convenience and its simplicity. Y prime evaluated at the point y equals 1, 0 is given by the matrix -2, -3, 3, -2 times 1, 0, which is -2 times 1 plus -3 times 0, or -2 in our first component, and 3 times 1 plus -2 times 0, which is 3 in our second component. So we have that the solution y that passes through 1, 0 is pointed in the direction -2, 3. And since the solution points up as it spirals into the origin, the direction of the spin at this point is counterclockwise. And as we stated above, since one solution points counterclockwise, all solutions must point counterclockwise as they spin into our equilibrium solution at the origin.